Hi, and welcome to the Astrotweeps Planetary Science Year-End Roundup. So, if you joined us last week for our astronomy roundup, this is the other half, the planetary science slash solar system sort of end of year wrap up with a bunch of your favorites, or some of my favorite planetary scientists who have been tweeting as Astrotweeps for this year. So, I'm Meg Schwan. I'm a postdoctoral fellow here at Academia Sinica in Taiwan. And I'm here with a whole bunch of people, and I'll let them introduce themselves, starting with you, Sandy.
Oh, okay, since I have the cold. Hi, I'm Sandy, or Alessandra Springman. I was at Arecibo Observatory in the process of leaving when I ran Astrotweeps at the end of June and early July. I'm now at the Lunar and Planetary Laboratory at the University of Arizona.
Cool. And you might remember a favorite face of Dimitri.
Yes, hi. I'm Dimitri Muna. I help run Astrotweeps. I work for the Sloan Digital Sky Survey, and currently I'm at OSU, Ohio State University.
Cool. And then next we have Brian Balta.
Okay. Hi, everybody. Brian Balta. I ran Astrotweeps in the latter part of the summer. I'm a visiting professor of petrology at the University of Pittsburgh, and I also tweet and run the Facebook/Twitter/other places page called The Earth Story.
Cool. And then we have Luke Dones.
Okay, yeah, hi, I'm Luke. I ran Astrotweeps earlier this month and talked about comets a lot, and I'm a research scientist at Southwest Research Institute in Boulder. It's very cold right now, although I'm at home, and I'm mostly interested in small bodies in the outer solar system particularly, and planetary rings.
Cool. Next we have Michael.
Hi, I'm Michael Ayer. I was doing the Astrotweeps also in the late summer while I was still a postdoc at UCLA working on lunar reconnaissance orbiter data. And since 1st December, I'm in Boulder as well, working at the LASP Institute on MAVEN data and Cassini ring data.
Cool.
Cool.
Welcome,
And last and not least is Phil.
Hi, I'm Phil Rosenfield. I'm actually not a planetary scientist. I'm a stellar evolutionary scientist who do stellar populations. Couldn't make the astrophysics one, so I thought I'd sit in and check this one. I'm a postdoctoral researcher at the University of Padua in Italy.
Very cool. So I guess to start off, we had a list of things we all sort of wanted to talk about, and one of the big things I think is that this was sort of the year of Mars and the year of comets in many, many ways. So I guess maybe to start is we've had a bunch of new things orbit Mars, both from India and the US. So maybe, Michael, do you want to talk a little bit about that this year?
About what? Sorry,
about MAVEN and Mars.
Oh yes. Sorry. Yes. So MAVEN is finally now in the science phase after some commissioning phase, where after arrival you check out the instruments and basically just trying to get into routine operations. And of course that was a little bit hard because just after arrival coinciding strings passed by, and that created a little bit of worries for the instrument because of the particle emissions that were expected by the comet. So NASA basically prepared every spacecraft around Mars to duck and cover, basically, and made press announcements with similar titles like that. And everything was fine. Not only was nothing damaged, to my knowledge at least, and on top of that, the science results are looking really promising. I'm working now with the IUVIS team, and the instrument lead, Nick Schneider at LASP, he made this nice joke a few weeks ago. He said, like, I like to be wrong with my predictions, and one of his predictions was that we won't see anything in our instrument from comet-siding spring. And he was beautifully wrong, because just when we came around on the other side and the instrument made a scan of the atmosphere, a limb scan, to check for certain spectral lines. As was shown in the NASA press conference, we found magnesium ion lines very strongly coming out. So we were sure that some material deposited from the comet actually had magnesium ions, actually magnesium and the ions, of course, created in the atmosphere. So yeah, I mean, that was some beautiful and very direct, simple results coming out of it. That's of course currently being further analyzed, but yeah, that was a nice result from that.
So do you want to talk a little bit what MAVEN is? You talked a little bit about Siding Springs, but what actually is MAVEN's job to do for Mars?
All right, so yeah, MAVEN is in basically the question is, why is the Mars atmosphere the way it is now, and why is it slightly different and so much thinner than the Earth? Even so, Mars kind of has enough mass to hold on to an atmosphere. It's on the limit. So people basically wanted to check what is the current status and what is the change of the status of the Mars atmosphere. So there are many instruments to look for particles itself, for the plasmas around it. How does the Mars atmosphere interact with the solar wind? And so it's a whole instrument sweep nicely designed around the whole question of how much of the atmosphere is currently escaping, and in high detail, magnetically and chemically, how is it interacting with the solar wind, the magnetic fields of the solar wind, and the particles of the solar wind. And it's mostly particles and chemistry instruments. And the one I'm working for is the only imager, but which is like a spectral imager. So it's can make a spectrogram, but over image lines, so it makes an image of it. So yeah, I think that's a okay summary of what MAVEN's job is.
Right, and so there's also MOM as well now, right? So that is the Indian mission.
Yeah, not too much is coming out from it. What I know from some colleagues that work in India is that the public communication is a little bit constrained because historically, like here in US, to my feeling, and to my information also, the Indian Space Organization is mostly done from a military point of view currently. And that's why the communication coming out of it is a little bit reduced. On the other hand, which we will maybe discuss later, it's also improvable on the European side, but that's a different issue. But what I wanted to say is, yes, impressive feast. They have less than $600 million less, I think they spent, and they arrived successfully and have science data. I recently have not followed it up too much. I don't know if anybody else can tell more about some science outputs that came actually out. But,
well, I think the exciting thing right now is, right, this is, you know, Mars has always been a Russia, Europe, America thing, right?
Yeah.
And so this is now, at least for me, I sat in a coffee shop and watched the live broadcast as MOM did its orbit insertion and like blacked out and came back, and I thought it was just watching the emotion in the room. Sort of, I don't know if anyone else watched it. Just the emotion in the room as people were waiting, white knuckling that moment, right, of it coming back around, and that it had sort of, you know, Mars is one of those places where there's a graveyard of a lot of robots that didn't make it. Mars is hard, right, as the saying goes. So I think that's sort of a testament as well, right, that they do have, you know, a spacecraft around there and starting to take science data. I mean, that's another group that is, you know, another country that's now doing that, another, you know, an exploring world. So for me, that's the exciting bit. I think is it may not have all the, you know, it may not be the most sophisticated mission. I think their point was to take some things, get it to Mars, and do some observations, and I think they're doing that. I mean, they have an imager, right? And so I've seen some cool pictures. So anybody else have any thoughts on sort of MAVEN and MOM?
Well, I just had a question about whether the issue of how big the nucleus of the comet was had been settled.
I didn't hear anything about it. But what I know from HiRISE is that it's clearly smaller than the Earth predictions. That's the last thing I remember.
Yeah, that's what I'd heard originally, and then at the DPS they kind of denied that, and then
Oh, really? Okay.
and then I was hearing again later, and I wasn't sure, if everything was synced up. So, okay, well, interesting.
Okay.
So I think I've got my screen share to actually show. Let's see if
Yeah,
it's showing.
we see an image. Yes.
Yay! I don't know why it wasn't working earlier, but this is the Maven should be the Maven observations of Sighting Spring. But I also have the image from HiRISE. So we talked a little bit about Comet Sighting Spring, but does somebody want, maybe Luke, do you want to give a little bit of context of why people were talking about Sighting Springs or why that was kind of exciting?
Yeah. Okay. So this really goes back to how much is in the Oort cloud. Of course, we've never seen comets in the Oort cloud directly. They're just inferred when they reach the inner solar system, and so you see these estimates that there are 10 Earth masses of comets or something in the Oort cloud, but that's based on the product of the number of comets we think are in the Oort cloud, which we might know to order of magnitude, and the average mass of a comet, which we might also know to an order of magnitude, but that's even less certain. And so this is actually the first time we've gotten a resolved look at a fresh comet from the Oort cloud, and so.
So Luke, what's the Oort cloud?
Oh, sorry. Yeah. The Oort cloud is the reservoir of comets far beyond the planets that has been known ever since Oort's famous paper in 1950. And basically, the idea is that when in the early days of the solar system, comets start out as small bodies, small icy and rocky bodies in between the planets, and most of them actually get ejected from the solar system by the giant planets. But a small fraction of them manage to reach a sort of quasi-stable orbit, typically at thousands or tens of thousands of AU from the sun. So the idea is that the giant planets scatter them into very big orbits that still pass through the planetary region. And then for a small fraction of them, the effects of the galaxy, just the general mass of the galaxy and passing stars, manages to lift the perihelion distances of some of them so that the entire orbit is well outside the planetary region. And then they can live for billions of years, and occasionally some of them get perturbed back into the inner solar system where we can see them.
Right, and so Sighting Springs is one of these interlopers that we're seeing on its first pass into the inner solar system, right?
That's right. That's right. And so what I was getting at was that people have said that the Oort cloud has a mass of tens of Earth masses or even more, and I've kind of been skeptical of that for a long time. Your colleague Ramon Brasser's work has recently shown that there probably are fewer comets in the Oort cloud than we thought, and so now if it turned out that this comet nucleus is really considerably smaller than we thought, then its mass is also going to be smaller. So I think it's conceivable that the mass of the whole Oort cloud is one Earth mass or perhaps even less.
But the thing about Sighting Springs, I think, is exciting is we got the size of the nucleus.
Right.
Because the thing came so close, right? So
it's the very first time, right?
The Sighting Spring is its first time into the solar system, so we're seeing it pretty pristine-ish for rattling around. It's been in the inner solar system, but this is the closest it's gotten, we think, to the sun. And so, in a long, long time, right? So, since it was put into the Oort cloud. But the thing was gone, so my understanding is Sighting Spring has come closer to a planet that we've actually been able to see than any comet that, in all the history of astronomy, has come towards the Earth. And so, for me, my mind's a bit blown on the fact that we had robots, orbiters, and stuff on Mars that we built, put out there, that were not designed to do this, to then go turn and look at this comet because it was the one shot as people who do team. Well, I guess we occasionally we call ourselves Team Outer Solar System, so the small bodies people being so excited about this, getting as close a look as we could to a comet.
That's right. It was great that we could all come together finally. But yeah, and I know this was a really hard observation, you know, Kristen Block and Kristen Schaller and so forth.
Michael, maybe you want to comment on that?
Just a comment that as Luke just started to say already, the observation was really hard because we had to balance the safety and the thrill of the moment. Don't wait too long before it's too far away, right? Because the further away it is, you reduce the resolution, and you want to be getting as best as resolution as possible. So I know that people at the spacecraft manufacturer company, I'm currently blacking out who it actually was. Yeah, I'm blacking out, but big shout out to these guys, because I know they started, they stayed up long hours on weekends as well to make this operation work, to get the data as soon as possible after the wake up, because there was the security shutdown of the spacecraft, and we needed the help of the spacecraft operator to get this running. And yeah, they joined the enthusiasm as any other scientists on the team, so that was a great thing.
So currently, hopefully, you can see on my screen showing up is the images of the nucleus from HiRISE, which is the highest resolution camera, I think, ever sent to any planet, but it's definitely the highest resolution camera that's on Mars that pointed and looked at the nucleus. And I think my understanding from the press release is you actually can potentially see jets coming out of the nucleus, but that this is a few pixels across, and that they with these observations, this nails the size of the nucleus better than anything we could do from the Earth. But HiRISE is not designed to do this, right, Michael? So this was a really hard thing to do, right? Because it's a push broom camera, right? So it's designed to look at Mars and use the orbit. So they have to do some kind of pointing, right, to be able to take these observations.
Yeah, that's actually an interesting fact. I keep forgetting that, because the operators on the HiRISE camera, they're so good now in making us believe that we just take a snapshot, but it's not actually happening. So as you said, it's a push broom camera, and for people who don't know what that is, you have a couple of lines. It's actually more than one, I think. Maybe it's 10. I forgot the detail. But it's not one CCD that takes one snapshot of the whole image. You have a couple of lines, and then you're pushing like a broom the camera over the object you want to integrate the light from. So everything has to be right. The timing, the exposure timing of these little lines of the CCDs, and your movement of this pushing over the object. And of course, all the timings, all the experience with the camera is done to observe Mars from an orbit 200 miles above the surface, roughly. And we know the light's there on the Martian surface, how much light gets back, how long we have to integrate. But this remote object, which was just a few pixels, that took quite some trial out, if I remember correctly. I'm not directly a member of the HiRISE team, but I'm a bit on the sidelines of the team for some polar observations. And I saw some test operations going on to try to figure out the rest observation times and so on, some test runs. And the quite nice resolving images were basically the result of dozens of test images to find the best timings. And yeah, it was certainly not easy, but I was unfortunately not on the TPS. If Luke has heard some more results of what they were discussing, maybe they had their doubts on some of the data. I only heard the last thing that yes, it's smaller than on Earth, but as you are closer, you must be resolving it better than on Earth. Well, depending on the instrument, of course, you use. But it was a good chance to resolve it better than on ground.
Yeah, so I think for me, still my mind's blown that things that we put around Mars basically nailed something that's in the outer solar system that now is informing sort of comet people, then these are, the people that study these comets and the building blocks for our solar system.
It's a mind-blowing set of lucky coincidences. I mean,
yeah.
That we are at Mars at that time with 3 active spacecraft, while this rare orbit passes by so close, and then that was really cool.
So for the non-planetary scientists, so Dimitri and Phil, what was your take on this as being someone sort of not quite sort of super excited about icy things and small bodies? What did your take of this sort of sitting on the outside?
For me, it's always impressive when you don't have a lot of data when it comes to the outer solar system like this, and to put all what you got to go right for whatever you got. So measuring the size of one comet nucleus really the fact that it can give you insight on the total mass of the system is pretty impressive to me. I mean, you really got to get everything you can out of the data. And so for me, it was not only was it the instrumental feat that we've been talking about, but also just that you can get that from this science is something that I wasn't aware of beforehand, because I haven't had a lot of experience in planetary science.
Cool. And Dimitri, for you, was this sort of interesting to hear in the news? Or, because for me, it was definitely sort of the fact that we're using things we put around Mars to do things it wasn't supposed to do. But as an astronomer, was there something sort of struck you about this story as it came out?
Not that specifically. I'm certainly impressed by the flexibility that these satellites and that these instruments have. We don't have the money and the resources to make them as completely flexible and to be able to do kind of whatever we want. And so for something that was designed specifically for Mars to be able to set its sights elsewhere, it's certainly impressive. And there have been a lot of results, which I think we'll move on to, comments and whatnot, that this year has really kind of drawn a lot of focus to things that happen in the solar system in really exciting ways. With data and high-resolution photos and things like that, I think it's really captured the public imagination. But I want to ask one question. So, if we have a limit or have an estimate on the size of one object's radius. So, to me, who doesn't know very much about planetary stuff, so I would kind of counter to that, saying, well, that's just one data point. How can we extrapolate from that one data point the mass of the entire Oort cloud, for example?
I guess I can try answering that. I guess the point is that we're going from 0 data points to 1 data point, so that's a big improvement. The issue really is that we do have sizes now for quite a few, meaning of order 10, Jupiter family comets, which is a whole different class of comets that that orbit the sun on fairly short period orbits, typically 6 or 7 years. And so what people have done in the past is assume that those properties could be applied to Oort cloud comets. And there are a couple of problems with that. One is, first of all, before we knew any better, people usually assumed that the density of a comet was equal to the density of ice, or maybe even a little greater. And now all the comets for which we have direct mass measurements, the densities are like 0.4 grams per cubic centimeter. So they're like half or a third the density of solid ice. So that's one piece of information we have. It's just that the Jupiter family comets have had a whole different history. They've been around the sun many times, whereas these new comets are, they have been in cold storage for billions of years, and so there's been some suspicion for a long time that they're actually brighter than a Jupiter family comet that is an object of the same size as brighter, because it has this sort of layer of super volatile stuff that kind of blows off the first time. And so, I agree, we still don't really have any good idea what the mass of the Oort cloud is, but at least we're starting to get some direct information that we'll eventually be able to use for that. You know, I'm a big booster of a I'm a big booster of a mission called Whipple, which is being proposed to Discovery again, and that, if it flies someday, will get occultation measurements of the sizes of Kuiper belt objects and things in the inner Oort clouds. So then we might really know what's going on.
I think that's a nice segue into sort of some of the other discoveries this year, which was the discovery of the second sort of confirmed inner Oort cloud object, 2012 EP113. Horrible license plate name, but it'll eventually get a real name. And so that object sort of is the second of these objects in the no man's land. So there's Sedna, and Sedna is this body that is too far away from the orbit of Neptune and too far away from the Oort cloud to really feel the effects. So it shouldn't be there. And it was this discovery earlier this year by Scott Shepard and Chad Trujillo nailed the discovery of a second object with a very similar orbit, which means that, which we'd always sort of suspected, was that whatever put these objects there would have to put a bunch of them out there. So for me, that was kind of exciting because my thesis was looking for more of these objects, and I didn't find any more. I only found Sedna, or well, I redetected Sedna. So for me, it was sort of exciting to find that we've confirmed another object that we are 100% sure is similar and probably was in place the same way. Maybe, Luke, you want to talk a little bit about Sedna and 2012 VP113?
Sure. Okay, so about a decade ago, Hal Levison and Martin Duncan and I did these models for forming the Oort cloud in the current galactic environment. So I'll explain what I mean by that in a minute. But basically, we just assumed that the planets, the giant planets, had the orbits that they have now, and that the sun was a single star, not in a cluster, and calculated how the Oort cloud would form. And this had been done, even in the 80s. We just did it, with more modern computers and algorithms and so forth. So what you find out when you do that is that there is sort of a gap. So you can, if you have a Kuiper belt, so things at sort of 40 astronomical units, things there can stay for the age of the solar system.
So like you can look on the image I'm showing, it's like those blue sort of dots there are basically represent the core of the Kuiper belt, and a whole bunch of other planetesimals get scattered out by Neptune in sort of orbits where they go out far, but they come back to that sort of bluish region.
Right. And so it turns out that you have one stable reservoir there, and the other stable reservoir, the Oort cloud, in the current galactic environment should have an inner edge with semi-major axes, so the average size of the orbit of 2,000 or 3,000 AU. And these objects, Sedna and VP113, are in neither of those populations. They have semi-major axes of hundreds of AU, but their closest approach to the sun is 76 or 80 AU. And that's basically impossible in the current galactic environment. You should not make any objects like this because they're basically too close to the sun for the current galactic environment, passing stars and so forth, to do anything to them. And they're too far out from the sun for the planets to do anything to them, for even Neptune to do anything to them. So they just shouldn't be there. So the idea that people have had, and again, Ramon Brasser has been working on this a lot, is that we now believe that most stars formed in clusters. So the sun might have been in a much denser environment by many orders of magnitude when it formed. So it could have been a cluster of 1,000 stars or even more. And in that sort of environment, the galactic effects, the effects of other stars have been a lot stronger, and it's a lot more natural to make objects like this. essentially the Oort cloud can extend a lot closer to the sun than it can if the sun just formed as an isolated star.
So we think a cluster might have done this, that the sun was in a stellar cluster and that stars would come in much closer by.
Right.
Then so the idea is that you need something else that scatters out Sedna in 2012 EP113 and basically detaches it from the planetary region. Because when you gravitationally scatter something, you come back to that point in your orbit. So that becomes a new point in your orbit. So if Neptune scatters you, you will have a closest approach close to Neptune.
Right.
Yeah, so something else would have to come by, swing by, and give you an impulse for you to pull that part of your orbit up.
Right. Right.
We think it could be that there was a star that came by when the sun was in a dense stellar environment. But the reality is we don't know. It could be that there was a planet that scattered it out there, and the planet's no longer there. It could be a single stellar encounter that one star came by. That's highly unlikely in terms of probability, but we really still don't know. The fairy tale story, which I think we all like to believe is the embedded cluster story, that the sun was born in a stellar cluster because many stars are born in it, but we really still don't know. I think we need many more of these objects to be able to decide. And so for me, the cool thing was that we now have the second one. Was that the same for you, Luke? Because that's what I was excited about with this discovery.
Yeah, no, for me, of course, I like the outer solar system, but yeah, I thought this was the most exciting thing this year. It was really great to see another one, and again, it's sort of amazing that kind of by analogy to using observations from Mars to learn something about comets, that now we're using a couple of these objects, in the Kuiper Belt or just outside the Kuiper Belt, and inferring where the sun was born. That kind of blows my mind too. And again, we don't really know yet, but it's as you say, as we get more of these, we'll have a better idea of what really went on.
Right. I mean, the reason is because these objects are dynamically isolated, so the hard bit that makes them hard to explain why they're there also means that their orbits are basically frozen in place. So if you can find more of these objects or orbits telling you how they formed or how whatever perturbed them onto these orbits, you can sort of read that archaeological record in the orbits of these guys. So this is the first time we've had two now. We've actually confirmed that the suspicions have been that there should be a population out there. We're now starting to find that. So I think it's sort of exciting for the next couple of years.
So are people expecting to find a lot of these, or really only a handful, or do we just not know?
We don't know. Because we don't, so it depends on what you assume for the properties. We think there should be a whole population out there because these are planetesimals. So as Luke will tell you that when giant objects scatter things, gravitationally scatter, you don't really need to worry so much about, on the small guys, they all kind of should go. So even though Sedna is dwarf planet size, about Pluto size, that's not the interesting thing. It's really its orbit. So we would expect there's a whole bunch of small planetesimals that should get scattered out onto these orbits. But they could be very dark. They will likely be on very elliptical orbits. They spend most of their time away from the sun, hard to see. My thesis put 10 to 100 times more mass than exists in the Kuiper Belt, sort of the remnants of planet formation out by Pluto, which is the thought is maybe there's 10th to 100th of an Earth mass out there. So there could be 10 to 100 times more than that sitting in this region, and we would have not seen it. So there's probably a lot lurking there. But this is, it's showing that it's now the observers have to go back to work and find more of these. And there's also a weird bit that there is suggestive evidence maybe that there's a Mars-sized or Earth mass body orbiting that's perturbing these orbits in a weird way. I don't know if, Luke, you want to just touch a little bit on that.
Yeah, this is a little tricky because I'm not an observer, but I mean basically there's an alignment in one of the orbital angles for all the bodies that have perihelion beyond. Do you remember Meg 45 AU or something?
Yeah, it's basically something like that. So all detached objects, all objects beyond that point that have their closest approach, not quite near Neptune, seem to show this effect.
Okay, so there's this sort of alignment, but alignment meaning they're all like within 60 degrees of each other. And it's the sort of thing you could maintain. If you could somehow produce this alignment, which I don't know how you do, you could maintain it if you had a planet, kind of an Earth mass or few Earth mass object out at a few hundred AU. And so Trujillo and Shepard showed that in their discovery paper for this stick, but it was just an example, and I don't think anybody has looked closely at what, the range of possibilities of, how much mass you would really need or where you'd have to put it to maintain this alignment.
Right. So I think it's an interesting hint, but it's not clear that there's a planet there.
Right.
So I think it means as the observers have to go back to work, it also means that theorists have to go back to work and figure out, is there other ways you can make this alignment that we don't know about? So it's an interesting hint, and then we need more objects. We got 2, right? We really have 2 I have a paper out that says we have 4 objects that we would say are in this inner Oort cloud region. So we need more than that, I think, to be able to answer it. But I think this year is sort of in the hint of we need to all go back to work on the Sedna region a little bit more, this inner Oort cloud. So I think the next few years will be exciting as bigger telescopes with bigger cameras go online and should be able to see more of these fainter objects. So I think that's a lot of small body stuff has been this year, and we will have to get to Rosetta because I think that's that's obviously the big story of this year. But maybe we want to talk a little bit about Earth. Just slide back a little bit and talk a little bit about water because it's a big theme of the Rosetta mission. But Brian, maybe you can tell us a little bit about this discovery of this, quote, ocean of water in the Earth's mantle, and so how we might not need comets to provide water to Earth.
Okay. This will or something else to supply water to Earth. Give me 1 second to Google a picture of the image of the inside of the Earth. Okay. Let's see. Find a good one. Okay.
Google's pretty amazing that it has it.
Yeah, why do we need all this seismology?
Someone Google high-resolution photo of that.
I'm going to come out ahead of time and say I am team Earth accreted wet.
All right. So maybe, Sandy, do you want to give the backstory a little bit while... oh, wait, Brian's got it up. All right.
Yep.
Yay!
Okay.
Yay, we got a picture of the mantle.
So, Meg said that this was that the outer planet Sedna region was her thesis. Water hidden inside of stuff was literally mine. So
Yay.
this is kind of my field.
Exactly.
Many of the minerals of the Earth's mantle can hold a tiny bit of water in them. We see the effects of this show up at the Earth's surface in subduction zones. We have continental crust, like you see hopefully in the image that I'm sharing, show up because at a subduction zone, a little bit of water from the ocean gets taken down into Earth's mantle. That reduces the melting temperature of the rocks around it, makes them easier to melt, and the end result of that is that we get volcanoes carrying that same water back up to the surface. This kind of creates a water cycle. Water from the oceans is being carried down into the mantle, and water is then coming back up from the mantle to the Earth's surface. Question we don't have a good answer to is what the balance of this is. There's a lot of ways to bring water in and out of the mantle where we wouldn't be able to track it because it just looks like water in the oceans. And one of the weird things we've discovered about the mantle, by taking the minerals that form the Earth and just squeezing them really, really hard in presses and heating them experimentally, is that olivine, the main mineral that forms the bulk of the Earth's upper mantle, turns into this other phase, this other mineral we call wadsleyite, when you get to about a depth of 400 kilometers inside the Earth. And olivine can hold a very tiny amount of water, let's say 0.1 or even smaller than that percent. Wadsleyite can hold a weight percent of water. It can hold 10 to maybe 100 times the amount of water that the olivine can hold. That means it's possible for there to be this reservoir of extremely wet rocks hidden inside the Earth, maybe getting water added from subduction zones, maybe holding on to water from when the Earth formed. it's always been possible, but nobody's ever known whether it's true, because the only way we could probe this area is with seismic data, with seismic waves that travel through the Earth. Until this research group working on diamonds from Brazil got this one really, really rotten diamond sent to them. You would never put this in a ring. It's gray. It's loaded with inclusions. It looks terrible. And they went into some of the inclusions in this very, very carefully. The reason this diamond's gray is that there's all sorts of minerals trapped inside it, and they found one grain inside one diamond from one place on the Earth that has this enormous amount of water in it, like 1.5 weight% water. So in one spot, we know that the Earth's mantle did get this wet. We don't know how that water got down there. We don't know if it was trapped from when the Earth formed. We don't know if this one diamond was sitting right above a subducting oceanic plate that got sucked into Earth. But we know that at least in one point, there's a whole lot of water down there. And that leads to all these other questions about where did this water come from? How early did you have to add water to get it down this deep in the mantle? And maybe how many other areas in the mantle are that wet?
Right, and so the thing is that we have questions about how the Earth got its water, right? So maybe
not just the Earth, but everywhere.
Everywhere, right? Maybe Sandy, you want to touch on this? You know, the thought is that where did our oceans come from, right? If the Earth formed already, you know, is this stuff locked in the mantle and it doesn't come out in large quantities? Where did our water come from?
So the idea is that Earth accreted wet, so we think Earth came from carbonaceous chondrites, and I think there are a couple in this room, but they're over there in the dark. And so that Earth formed from this very primitive material that hadn't been heated a lot, it hadn't been processed, and this carbonaceous chondrite material is pretty much very similar to the early solar nebula composition. And so it has a lot of water tied up in it and hydrated minerals. And so we assume Earth formed from carbonaceous chondrite material. And so therefore Earth accreted wet. And that a lot of this water can be still locked up in the mantle, up to tens of Earth oceans. And so some people say, oh, comets are responsible for all of Earth's water. But for some comets, these deuterium to hydrogen ratios just don't match up with what we see for Earth water. So it could be that comets delivered some of Earth water, but really it's quite a lot more likely that Earth accreted with most of the water it has today.
Or the other suggestion is that there's the reservoir as well of the asteroid belt. We know that there are these things called main belt comets. So they're asteroids that have a small reservoir of water ice that they look like comets. Some of them basically have activity because there was a collision exposing some of this water ice. Other ones are cyclic, and so clearly there is some kind of mass shedding or loss of water. And so I guess there is some debate still whether you can get all your water from the Earth formation, whether you can get it from the comets, or whether you can get it from the asteroids. As Sandy was touching on, saying that you could get it from the Earth, which I think that's kind of an interesting sort of take, right? Because one of the problems, as you said, is this D to H ratio. Brian, do you want to try to explain what that is?
So I want to jump in and say one thing first, and that's that it would seem really easy to explain how you could have the Earth keep all of its water from water-bearing meteorites, except we have this moon. And the moon seems to imply an extremely energetic impact late in Earth's history, and it's really tough to figure out ways the Earth could keep water during that impact from beforehand, unless the Earth was able to trap some of the water in its mantle. And finding a really wet piece of the mantle might fit into that story. The other tool we may have that we might be able to use to track this, and I want to add as many caveats as I can, I said may and might, and we'll add a few more if need be, is deuterium to hydrogen ratios. Deuterium and hydrogen are two isotopes of hydrogen. Deuterium has 1 neutron, so its mass is twice that of hydrogen. And it kind of gets treated like a fingerprint of what was used to make the water reservoirs on objects. Because in order for an object to have a certain deuterium to hydrogen ratio, it has to have gotten an amount of deuterium, gotten an amount of hydrogen, and then processed that in some way. So the game that people have tried to play with deuterium to hydrogen ratios is, if we find a reservoir of comets that seems very, very close to the D to H ratio we see in Earth's oceans, or we see a reservoir in asteroids that seems very, very close to very, very close in D to H ratio to Earth's oceans as well, then maybe we have a match that we might be able to say Earth's reservoir of deuterium to hydrogen looks a whole lot like this. Or Earth's reservoir of deuterium to hydrogen looks a whole lot like the reservoir from comets or asteroids. The same game gets played on the moon as well. The problem with doing this is that deuterium to hydrogen is one piece of evidence, and it's really, really complicated. Because deuterium and hydrogen can move around in the early solar system. You can burn off hydrogen and leave behind deuterium in a planet's atmosphere. We actually see this on Mars. Mars has a whole lot more deuterium in its atmosphere than Earth does as a ratio, probably because Mars lost most of its atmosphere. And let's see. So people do this on Earth, and they played this game with one of the Jupiter family comets that was measured in 2012. I don't remember the number. Maybe somebody does.
We'll get to the comets because
Okay.
It's a good segue.
That's what I was trying for.
Yeah, you're leading to.
That was what I was trying to set up.
Perfect, because I have the plot for you, but I think we need to talk about Rosetta before we show the plot, because the plot thickens. But the plot that we're talking about is this D to H ratio for comets, and the big, I think, comet story, and maybe the big astronomy story this year, at least for me, has been Rosetta and Philae and going to Cheremeyev Gerasimenko. I hope I got that right. I think it's close. Which is the
Dumov Gerasimenko.
All right, we got somebody who can do it properly, more better than I can. So this is a European-led mission. I don't know if Phil, you're in Europe, so maybe you want to talk a little bit about ESA briefly, but it is this mission that is going to a comet, and one of the goals was to try to figure out where Earth's water is coming from by sampling another comet. So, this is a orbiter and a lander that went to, they woke up earlier this year and went to the comet. And I mean, it has had a lot of surprises, starting with just, if you're seeing on the screen, you should hopefully be seeing the comet. And it looks like a rubber duck. And it shouldn't have looked like a rubber duck from what people expected from ground observations. So already the shape of this thing is confusing people, and bringing more questions than answers, which is exciting. And so Rosetta is the orbiter, and Philae was the lander that successfully landed, bounced, and landed, and bounced and landed on a comet. And so one of the things is to study this D to H ratio as well as other things and probe the surface of the comet. Phil, do you have any context, or do you want to give any sort of idea, sort of your feelings on this?
On landing on it from the ESA perspective, I'm not really in on the administration. I'm American, so I've only been in Italy for about a year and a half, and so I really wasn't hip to how it was administrated, but it was a huge event in Italy. There was about 5 days of PR. It was really exciting, and it was a huge success from where I stood. But that's about as much context as I could give from the admin standpoint.
Cool. Well, I think and so I think for me this is this is big because it's NASA has done lots of things, right? But this is a big, daring, and scary mission right? That like was daunting and testing technology and hard, right? Space is hard, and they did it, right? So I think maybe for all of you who watched, at least for me, kudos has to go to Emily Lakdawala and Chris Lintott because they were there covering this and tweeting like this all the way to the end. So I followed basically on Twitter as well as whoever does the Philae Mupus account, which is one of their probes. Like they were tweeting like preliminary science results the day this thing went, like the day this lander shut off. So just to sort of give some context, Sandy, do you want to sort of talk a little bit about the mission and the lander?
Sure. So this mission, what year was Rosetta launched? It had been going for a long time. The technology on board, 2004. So it had been going for 10 years before it finally pulls up to this comet, and it matches up with the orbit of Churyumov-Gerasimenko. And it was interesting because Steve Lowry and some other folks had gotten Hubble time a number of years ago to try to get the shape of this comet ahead of time. And they got what sort of looked like a kind of an oval stress ball. There's these star-shaped stress balls that they hand out at LPSC, and it looked a lot like this comet model. And they got the size right, but they really didn't get the shape. So the Rosetta mission planners were expecting to land on this sort of spherical round comet, and instead they landed on a rubber duck. So they roll up at this comet, and it's these two things sort of stuck together, and it's got this neck, and it has sand dunes, and it's very fluffy, and it's really not at all what they were expecting, which is the great thing about the solar system. It's always full of surprises. Excuse me. And so they have this lander, Philae, and Philae was launched in November during the middle of a planetary science conference here in Tucson, and it was a lot of fun to be in this room with folks and everyone watching on Twitter as the live feed dies in front of us. Dimitri just got whacked by a cattail. Comets are like cats. They have tails, and they do precisely what they want. And so Philae landed on this comet, and it had a harpoon, and it had a drill, and it had all these things. But the problem was that it bounced on this comet, and it bounced at least twice on this comet. Okay, so it bounced a couple of times, and so it really, each bounce was about a kilometer.
So just to show sort of the context of the images on the screen is from the OSIRIS imager, the high-resolution imager, and it actually caught, they didn't see this during landing, but they actually caught this thing. The OSIRIS imager actually caught this thing, like Philae bounce and sail over to where it ended in this crater. So that's the image going on, is the sequence showing it at the end, going into it sort of the crater wall where it's.
So the mission planners had this idea that they would land Philae in the specific area, and it would be great, and there'd be sunlight for the solar panels and all that, except no, it lands in this crater, and they didn't know where it was for a while, and it's dark, and so its solar panels couldn't collect enough energy, so the batteries have died. So maybe it'll wake up in the spring when the comet is at a slightly different orientation compared to the sun, and life will be great. But Philae got, there's no magnetic field. It measured all sorts of interesting things about the composition of the interior of the comet. There's a ground-penetrating radar involved. So it's been really neat that we found out all these things about comets that we really didn't know before. And we really had a couple of surprises, too. And some people, there's been an idea for a mission for years for this comet hopper. Well, at least Philae has proven that this concept is viable, if not entirely precise.
Right, and I mean, I think the exciting thing is, even though Philae isn't active now, it got 80% of the primary science done before the batteries died. So there's a lot of data that came out of Philae, even though it's no longer active right now. And hopefully, if this comet's coming closer to the sun, it will get warmer and sunnier, and hopefully recharge the batteries. But for me, this is kind of exciting because it all played out on Twitter. Like in live time, people were tweeting results, like Chris Lintott and Emily Lakdawala and BBC. People were there, and the teams as well were like tweeting to each other that like the Mupus probe, which is their multi-purpose probe, like tried to use its hammer into the surface, like at the last-ditch efforts of like they knew they were going to be out of power, so they were going to just use it and see what they got. Like the surface was too hard; it broke the hammer. And those results were released pretty shortly after the spacecraft shut down, or the lander shut down. So I don't know if for any of you guys, did you have a perspective of how you were watching and learning about what was going on with Philae and Rosetta.
I was live online all the time, and it cost me lots of hours of sleep. So in US, it was the most exciting times were always after midnight in US. And yeah, I know some people of the team, so I was quite closely attached to it, even so I'm not a member of the team. And I agree with you, the Twitter streams were just so exciting because you actually could see different instrument teams from the Rosetta lander asking each other questions via Twitter because it was just faster communication. I remember that at the time there was the belief that maybe the inclination of the lander is quite high because Biebring in the press conference said that one leg points to the sky, and we didn't know how much it points to the sky. And then Mupus used some of this hammer, and people were starting to get worried. You know, can it not fall over that whole thing when you use this, and what happens, and so on. So there was just details of this emergency operation planning that not everybody got, and you saw some of the instrument people asking via Twitter. So what exactly are you guys doing now, and things like that. So that was kind of cool to see that, and I think this is very promising also for the general public who pays the bill of all of this. They are really this way. They're really in touch with what's going on, and I find this really exciting and really important. And what else? One thing I wanted to mention: the gravity of this little thing is so low. It's actually interesting to think that it's less of a landing. One of the team members, Carsten Seiferlin, he always made presentations showing the comet the upside down. So hanging from top and then showing graphics of how the lander would attach itself to the comet, which is really the better thing of thinking about this. And that's why it was such a big problem and issue, and this guy's jumping around once it was unlucky that the harpoons didn't shoot.
Well, we should step back and explain why, which is that there's so little gravity because these things are so small, right?
Yes.
They've shown images of like this comet next to, London and Boulder and all these places that there's so little gravity that basically it needed to harpoon itself in to really stay on. Exactly. And the harpoons didn't work. They knew that, and the harpoons failed. And also their thrusters. So they knew that there was going to be this thruster that was going to help try to hold it down while it harpooned itself, and those didn't work. And so there was a moment where there was a no-go about because they knew the thruster didn't work, whether they were going to try landing anyway, but the harpoons then failed. So those are the things that were kind of supposed to stop it from bouncing, because it's basically, there is so little gravity that any little kick is holding it up, as well as the ice screws. Dimitri has the 2 scale. What city is that he's sending me?
I've seen it behind several cities. I think it was also behind New York, or on top of New York at some point.
So, let's see if I can get it up.
Yeah, so it's really more of an attachment process than a landing. So you really need to attach that lander to that little feeble surface.
But I mean, I think it was an amazing success for ESA, and
Definitely.
We always talk about the daring things. I think with NASA, and like this was daring and risky, and is producing awesome science. And there's lots of things to come from the lander later, right? People are still processing data and probably catching up on sleep. But there's also the result that just came out, and where Brian was alluding to was the D to H ratio for this comet is out, and it doesn't look like Earth at all.
Yeah, I was actually wondering if people can comment more on this story, because when I was in Bern, and there's a lot in Bern, Switzerland, working there's a lot of commentary people there, and they were talking about, at that time, that was 2006, that the water story is completely up for grabs now. Nobody understands anything. Where does the bloody water come from? Now people start talking again that maybe it comes a little bit from comets.
Well,
So,
so here's the plot.
yeah, so
Here's
where
Earth
does
on
the
the
water
line.
come from?
Here's asteroids that are on the line. There's Enceladus, which is a moon of Saturn. There's all these Oort cloud comets that are higher, Jupiter family comets. There are two that are on close to the line. And then you have our friend Churyumov-Gerasimenko 67P, which is the Rosetta comet, 3 times above Earth.
He just likes to be special in everything.
So
So, a couple useful things to know about this plot. If you notice down at the very bottom, you see the protosolar nebula. That's just gas from the solar system that went into forming the sun. That's why Jupiter and Saturn are so far down there. They picked up a lot of the same gas that formed the sun. All the rocky bodies, all the asteroids are heavier. They have a higher D to H ratio, so they're higher on this plot. That means that they have more deuterium to hydrogen than the protosolar nebula, so they can't have gotten their water from the protosolar nebula alone. Earth doesn't really look necessarily like, it looks like some asteroids, but not all of them. Earth doesn't look like the Oort cloud. The Oort cloud has generally way too high of a D to H ratio if you see all of the pink points in the middle. Then there's these family of comets that go out to about Jupiter's orbit and come back, the Jupiter family comets. Somebody can correct me on that who knows comets better. And in about 2012, I think it was, we got a D to H measurement of the comet Hartley 2. And suddenly we had something other than asteroids plotting on that horizontal line that looks like Earth, which meant, hey, maybe we have a cometary reservoir that could supply Earth's water too. Then we get this one. This one looks nothing like Earth again. It has, again, a higher D to H ratio. And it's real easy to move up on this plot. It's hard to move down for a planet unless you're adding in asteroids or the solar nebula. So that means that there's at least a puzzle here. There's several puzzles, actually. One, where does Earth's water come from? Is asteroids the only thing we have left? And two, why do the Jupiter family comets look different from each other? That
Right.
was mentioned in that paper, and they don't give a good answer to that, as far as I could tell. Is they just kind of say, well, they look different, and why? Okay.
I think it opens more questions than answers right now, which is that there's a weird variety. So the source of the Jupiter family comets is thought to be the Kuiper belt, right? So I don't know if you want to just in 2 seconds, Luke, give the brief overview, right? Which is these things come from disks because the dynamic shows that Jupiter family comets likely have to come from the Kuiper belt.
They have low inclination, so they basically have to come from a low inclination source, which we think is probably the Kuiper belt. But also with the infamous NEASE model and other models of planetary migration, we now think that both the planets and the small bodies moved around quite a bit. So the regions where the Oort cloud comets and Jupiter family comets form probably overlap quite a bit. So it would be surprising if there were a huge systematic difference in their D to H. So the new detection, the CG one, is actually kind of reassuring. It would be weird if they were all like Hartley 2.
So
Just lower than the Oort cloud.
So yeah, so I think we still need some more measurements too as well. So we've now got 3 samples, but 3 times the Earth ratio is high, at least very high, higher than I would have thought it was going to be. So that's kind of, Rosetta's been the big thing, but since we're running a bit over time, and just sort of to end on one of the big stories that just came up recently is the methane on Mars. So maybe, Michael, do you want to briefly talk about it? Or Brian as well, I think you two might be the best to talk about this methane on Mars story.
Well, just a few numbers and the history. Somebody, Mummer, Dr. Mummer, he made some observations from Earth and saw a lot of methane, and it was even temporary variable because next time he looked, it was not there anymore. So methane story always is the problem. You first have to create it and you have to destroy it. It has to come and it has to go away. That's the big issue with methane. So then Curiosity landed and confirmed there was nothing there, so that story died out since last year. And they figured out the background is zero point 0.7 parts per billion as a standard background. And then some instruments saw it and saw some methane popping up again, but again temporary variable. So and it was a number of 7 ppm, so 10 times over the background. And if something is 10 times over background, usually your the data taking is good enough that this is not noise anymore. It can't be explained with a random event. So
and the used a plot up that shows that. So it shows that there's these 2 spikes that last a good number of sols or days on Mars, and that they observed. And Brian, maybe you can comment on this as well, but we shouldn't have methane in the Martian atmosphere.
Yep.
So what are the things that could be producing it? Because it should be getting destroyed. So if you're seeing methane, it has to be recent, right?
Correct. You can have a bunch of sources of methane. There's ways to make it without biology. There's reactions that can happen between flowing liquid water and rocks that produce methane. You can have volcanoes, volcanic rocks, that actually spit out small amounts of methane. These are active sources that can give that off, or of course biology can give that off, but I don't even know if we're allowed to talk about that one. So something gave off a pulse of methane above the background that lasted for a period of about 2 months, was easily measured by Curiosity, and then went away. And methane won't last in Mars's atmosphere. It doesn't even last that well on Earth because biology uses it up on Earth. Where this methane is coming from, therefore, is a very interesting question. And conveniently, the European Space Agency has for a while been planning a mission to Mars known as the ExoMars Trace Gas Orbiter, or Trace Gas Explorer, that in no small part was built to go and measure variable methane in Mars's atmosphere and try to figure out where it's coming from. And when the Curiosity rover landed and couldn't detect any methane for its first 300 sols, this made me worry that we were building a mission or that the ESA was going to run a mission for nothing. We have something to measure, so I now really want to see the results of this instrument if it flies in a few years.
Right, because what's producing this methane?
And where is it coming from?
Right, so it could be geologic. It doesn't mean that there are cows on Mars. Doesn't mean there are bacteria on Mars, but that is, life could be one thing that could do it, but it could be easily geologic. So I think that was sort of the very recent results, the exciting thing that was coming out of Mars and Curiosity.
Oh, and one more thing. If anything is generating methane, even some geologic process, the ability to use up methane is something that life is really, really, really good at on Earth. And life on a different planet being supplied with methane as an energy source would probably also find that really, really, really useful. So if there were some source of geologic methane on Mars, that is a food source that could keep life going, even in a very remote, obscure environment.
So Mars has got it maybe a little bit more exciting for the prospects of finding life in our solar system outside of Earth. So we're about over time, so Sandy and Phil had to go. But do we want to just wrap up with what your biggest sort of event was for this year in planetary science? Maybe Dimitri, just run through everybody. Dimitri, do you have something, one story or something we haven't touched on? What was your sort of big thing for planetary science or solar system this year that you felt was the #1 story?
Oh, easily the big thing for me was, holy crap, we landed on a comet. We can do that. So yeah, that just captured everyone's imagination, and I was riveted to my Twitter stream as well. So I think that, hands down.
What about you, Brian?
Oh, I gotta say the comet landing also. That happened right before I gave a lecture, and that was the best lecture I gave of the year. And it's nice to get a result out of it that I'm actually interested in already, which is the D/H ratio.
Nice. What about you, Luke?
Yeah, I think the comet landing's got to be #1. Although I did want to also mention, the new quote Sedna and the ring around Chariklo, which I don't think we mentioned, which appeared in the same issue of Nature as the new Sedna. So it was really, really interesting week.
Yeah, it was. What about you, Michael?
For me as well, I want to explore the circle a little bit though. So to spacecraft operations. I mean, I think this year was really a good example of how the engineers of spacecrafts and the scientists work together. Because another example of excellent timing and operation was the comet sighting string satellite protection phase, followed up by direct scientific observations. And the comet landing is just another example of this. How we really have people of all the different fields working towards the same goal, and what we can do this year. Another example, I think, is the Orion capsule and the technology on this new spacecraft of the US. How they have live HD video streams on this stuff, and I mean, this is just unbelievable. You can watch everything going up to space and coming down in one piece. This is just great.
It is
It's
very cool how
SpaceX
live time everything is. I think for me, hands down, comet landing, or attempting to harpoon a comet. Second has to be, and we didn't talk about it, was that we found a habitable rocky planet. Well, we found a rocky planet in the habitable zone of an M star. So the Kepler team and Lisa Quintana, who led the paper, I think that was kind of an exciting result as well, that an exoplanet is pushing into these planets where we know they're rocky and maybe potentially, if we know the atmosphere, could have liquid water. So sort of maybe water is the theme, at least for me, for this year, frozen and liquid or otherwise. So I guess with that, we're definitely over time. So I just want to thank all of our panel, and if you just, since you guys summed up, just if you have anything you want to plug, now's the time to do it. So, Dimitri, is there anything you'd like to plug for the viewers or for next year?
Well, if you're seeing this, you're probably watching or following Astrotweeps. Invite some friends, and if you're an astronomer, please sign up. We still have slots for 2015 to host Astrotweeps for a week.
What about you, Brian? Anything you want to plug or mention?
No, I'm good.
What about you, Luke?
I'll cut it right there.
I wanted to mention, Cassini has almost 3 years to go, and we're going to get some amazing data at the end of the mission, flying right over the rings, getting the mass of the rings, and getting some amazing high-resolution images.
Very cool. Anything you want to plug, Michael?
I'm very excited about New Horizons. It will arrive next year to Pluto, and had a successful wake-up event in December. So people should stay tuned. I mean, to have a flyby at the furthest away, so long known body of the solar system, I mean, that's really exciting.
Very cool. And so Dimitri already plugged Astrotweeps, so I'll plug one of my other projects. Actually, Michael's on the science team for it as well, is Planet 4. So it's a citizen science project using images from the high-res camera to map these seasonal fans on the south pole of Mars. So we need your help. You can go to planet4.org and help us explore Mars and better understand its climate. So I think with that, we'll wrap up and just say thank you to everybody that participated, and thanks for watching, and follow Astrotweeps at Astrotweeps on Twitter. Thanks, everyone.
Right.